Okay, for this last section, we're going to just take a quick look at some interesting properties of geometry. If you choose to take any geometry classes in college, you could expand on this quite a bit. There's whole classes on some of the topics that we're about to discuss. But ultimately, the first part is this idea of graph theory. We had the Swiss mathematician Leonhard Euler, and that is pronounced Euler, not Euler, proved that it was not possible to stroll through the city of Königsberg, Germany, by crossing each of the 7 bridges exactly once. If you take your pencil and you start at any of these bridges and you try to make your way around the city, okay, crossing each bridge exactly once, okay, it turns out that you can't do it. Ultimately, this opened up a new kind of geometry called graph theory. So we're going to start out with some vocabulary words regarding graph theory, and the first one is a vertex. Okay, so a vertex is always going to be just a point. An edge is going to be a line segment or curve that starts and ends at a vertex. So if we have two vertices, a vertex here and a vertex here, okay, and we connect them, whether it's a curved line or a straight line, okay, this right here is the edge. Okay, so this is the edge. These are the two vertices. We generally label them V1, V2. Okay, if we want to label the edges, we'd label that edge 1, etc. And ultimately a graph, okay, unlike a graph on a coordinate plane like we're used to, a graph consists of vertices and edges. So what I've drawn right here is a graph. Okay? And then part of the idea that we're going to study in just a second has to do with even and odd vertices. Okay? If we have an odd vertex, it has an odd number of edges. Both of these would be considered odd vertices because there's only one edge that's going to this vertex, there's only one edge that's going to this vertex. Okay, if I were to introduce, let's say, 3 of them, and have a graph that looked like this, say V1, V2, and V3. V1 and V3 would both be odd degree, but whereas V2 would be even degree because it has 2 edges that are connected to it. So it would be considered a degree 2 vertex because it has 2 vertices that are attached to it. Okay. All right, so what we're going to look at next is traversability. This gets back to that Königsberg bridge problem. So ultimately a graph is traversable if it can be traced without lifting the pencil from the paper and without tracing an edge more than once. Okay, so we can't cross an edge more than once, okay, and we also can't lift the pencil off the paper. So here's some rules for whether a graph is traversable or not. So a graph with all even vertices is traversable. Okay, one can start at any vertex and end where one began. Okay. A graph with 2 odd vertices is traversable. One must start at either of the odd vertices and finish at the other. And a graph with more than 2 odd vertices is not traversable. So let's go back to the Königsberg bridge problem. If you look at the number of edges that hit C, there's 3 there. 1, 2, 3 at B. 1, 2, 3, 4, 5 at A. 1, 2, 3 at D. Notice that there are more than 2 odd vertices here, so that makes this graph not traversable. Okay. If we were to add a bridge somewhere, we could make it traversable possibly, okay, but in this particular case, there's more than 2 odd vertices, therefore it's not traversable. That's what you're looking for with traversability. Okay. So let's take a look at this graph. So is this graph traversable? We can see that the vertices, and this is what you want to do right away, is just count how many. 1, 2, 3, that's odd. 1, 2, 3, that's odd. And this one only has 2, so that's odd, or that's even, that is. So we would say yes, because our rules say, number 2 rule says that if there is 2 odd vertices, then it is traversable. But to traverse it, you need to start at one odd vertex and end at the other one. So they've illustrated such a path here. If we start at this one, okay, and we go, let's say, down here to this one, up here to this one, across this way, and then around that way, we will have went over every edge and not more than once on any given edge. And again, we started at one odd vertex, we ended at the other. Okay, so that one is traversable. All right, so the next topic we're going to talk about is what we call topology, which again, some of these topics are entire classes in college that you could take, which you might find interesting. So they're generally not terribly hard, but they're some interesting topics that you may have never studied in math before. All right, so objects are classified according to the number of holes in them. That's called their genus. Okay, genus is the number of cuts that can be made in the object without cutting the object into 2 pieces. And if 2 objects are topologically equivalent, they have the same genus. Okay, so topology of knots is used to identify viruses and how they invade our cells. Okay, so one of the uses of topology in real life. Okay, so let's take a look at a couple pictures here. We have 3 shapes below have the same genus. It's 0. No complete cuts can be made without cutting these 2 objects into 2 pieces. Okay, notice that they have no holes in them. Okay, so their genus is 0. Whereas if we have a donut and a coffee cup, they have a genus of 1. Okay, because there are holes in them. There's a hole in the donuts and there's a hole in the coffee cup at the handle. Okay, so we say that those have a genus of 1. Okay. If we take a bowling ball, for instance, which has 3 holes in it, this one's a tricky one because ultimately when we think about holes, okay, there are holes drilled in a bowling ball, but are they actually holes in the bowling ball? Okay, they go into the bowling ball, but do they go all the way through and actually make a hole? Okay, the answer is no. So a bowling ball is going to have a genus of 0. Okay, so even though it looks like it should be 3, unless those holes go all the way through it, okay, then the genus is still 0. Okay. Alright, a couple other things I want to look at here. Comparing, there's 3 systems of geometry. We have studied in our work so far, we've studied Euclidean geometry. Okay, and a couple of key points in Euclidean geometry is given a point that's not on a line, there is one and only one line through that point that's parallel to the given line. Okay. And the geometry of a plane, when geometry is on a plane, when we talk about Euclidean geometry, we have another type of geometry called hyperbolic geometry, and the parallelism in this one is given a point not on a line, there are an infinite number of lines through the point that do not intersect the given line. Okay, and ultimately the geometry here is on a pseudosphere, which is a shape like this. Okay, and then elliptic geometry, okay, is that there are no parallel lines, and the geometry is on a sphere. Okay, we're not going to spend much time on this. I just wanted to introduce it to you so you saw it. But there, like I said, there are whole entire classes on non-Euclidean geometries, okay, which ultimately change the rules that we've used over the past few years. Okay. Here are a couple of rule changes here when we're dealing with the non-Euclidean geometry. We know that with our geometry, when we're on a plane, that if we have a triangle, the sum of all the angles in the triangle is 180. Okay, with hyperbolic geometry, the sum of the measures of the angles in a triangle is less than 180. Notice the picture here on this shape that we deal with. Okay, and ultimately in this elliptic geometry, the sum of the measures of a triangle are greater than 180 because we could have 2 right angles here and another angle, which ultimately would be greater than 1 angle. So like I said, we're not going to do too much with that in this class, but ultimately I wanted you to see it. And then the final topic here is what we call fractals, another vast topic that you may or may not study at some point, generally involved with computer programming. Okay, this is like a geometry of natural shapes, self-similarity, for instance, if we look at the fern leaf here and the similarities that we have. Okay. So a couple of vocabulary words involved with fractal geometry is that we have self-similarity. Is the quality of smaller versions of an object appearing within the object itself. Okay, so if we take a look at this triangle, notice that we have a whole bunch of little triangles as we make our way down to smaller objects. Okay, and then an iteration is the process of repeating a rule again and again to create a self-similar fractal. Okay, so we're not going to create any fractals ourselves, but like I said, I want you to at least have an idea of what a fractal was as you exit and move on to college.